Edit round of GamesNet. So today we have Zaccour, who holds a chair in game theory and management and the professor of management science at HEC in Montreal. He holds a PhD in management and an MSc in international business from HEC and a license in mathematics and economics from Paris Dauphine. Oh, nice. He served as the director of Gerard, marketing and a PhD program at HEC Montreal. His research areas are differential games, optimal control and operations, areas in which he has published over 100 papers and co-edited 13 volumes. He co-authors the book Differential Games in Marketing and Games and Dynamic Games, which is scheduled to appear soon. His research has been funded by Natural Sciences and Engineering Research Council of Canada. He's the editor-in-chief of Dynamic Games and Applications and an associate editor for several journals. He's a fellow of the Royal Society of Canada and was president of the International Society of Dynamic Games from 2002 to 2006. With that, George, the floor is yours. You can pause to take questions, or you can let people ask questions when they want. In fact, it might be easy if somebody types they have a question in chat, and then you can see that, or I can tell you there's a question, or somebody will tell you there's a question, and you can take a pause and field the question. So with that, it's up to you.
Okay, thank you, Sudipta, for the introduction. Thank you for inviting me to be part of this very nice series of seminars. I feel really honored. When I got the invitation, I was asking myself what kind of thing I can present, but I decided to do something which is rather of tutorial nature, given the composition of this group, instead of presenting my last paper and digging into proofs and things like that. Now, regarding questions, please interrupt me whenever you like. I would be happy to take them. Okay, so I'll be talking about sustainability of cooperation in a class of stochastic games. This is the agenda. I will first give you some background about the issue itself of sustainability of cooperation, and after that, a short background on dynamic games played over event trees. This is a kind of special class of stochastic games. And next, I will show some results. I have, I think, 42 slides. Probably I will not be able to go through all of them, but since the slides will be posted on your website, I felt it's better to have something a little bit more complete. Okay. So as a motivation, the first thing that we can notice is that in many areas, agents or players are signing long-term contracts. Examples of such contracts are union and management. For instance, they may sign a contract for 3 years or 5 years. International agreements are also long-term contract in principle. So one natural question is why to commit? Why do we need to sign long-term contracts instead of signing a contract every day or every minute or every half an hour? The answer is twofold. One is that there is a negotiation and contracting cost, and we can minimize this cost by having a long-term agreement instead of repeatedly negotiating. More importantly, I would say that it's a question of vision. If you consider, for instance, climate change, if you have a very short-term agreement, you will be looking at only today's cost and benefits, and probably you will end up not making much painful decisions, but necessary decisions. So by having a long-term perspective, we can start implementing some right decisions right away. So it's a matter really of vision. Now, given this, we know very well that some agreements are breaking down before their maturity. This means, in my terminology, that the agreement is time inconsistent, meaning that we are signing an agreement at instant of time 0, and the agreement is supposed to be in place till time capital T, but for some reasons, the agreement is not carried over till its maturity. This idea of time consistency has been discussed in the literature under different terms like sustainability, dynamic individual rationality, dynamic stability, durability, agreeable solution, and so on and so forth. Now, we know that long-term contracts exist, we know why we should commit, and we know that they break down at least occasionally. So now the question is, can we do something about it? Can we design mechanisms, side payment schemes, such that we ensure durability of these agreements? There is a very large literature in dynamic games regarding the implementation of sustainable solution or sustainable cooperation. For instance, you have the whole area of cooperative equilibria, where players would implement trigger strategies that are strategies based on past actions that include a threat to punish credibly any cheating on the agreement. And in different classes of dynamic games, a lot has been done. For instance, in repeated games, we have a long tradition, we have Folk's theorem. Similarly, in stochastic games with Duta Folk's theorem in 1995, and in differential games, we have also a series of results. Tolvinsky, Ori, and Lightman are probably one of the first to report such results in state space continuous time games. Now you have a lot of this in the book by Dockner, Jorgensen, Long, and Sorger, and also in my book with Alain Ori and Jacek Krawczyk, covering these ideas of cooperative equilibria in differential games. One particular strategy that has been followed in order to sustain cooperation is the so-called incentive strategies. This is a case where we can do something about durability of an agreement, but only in a two-player framework. So suppose that the two players agree on implementing U1 star, U2 star. Now, the way it is sustained is through the so-called incentive strategies, here where player J is indexing her strategy or decision based on what the other player is doing. So here the incentive strategy is written in this way. This is the simplest case, but it can be much more sophisticated. So player J is promising to play her part of the agreement plus deviation. And this deviation, here you see it depends on the deviation of the other player and a penalty term. So if the other player is a gentle person, meaning that she is implementing the same thing in the agreement, this element would be equal to 0, and the best response would be to implement also the agreement. A series of papers by our friends from Helsinki, Tamo and Hamalainen, dealt with this idea of incentive strategies in differential games. There are two issues here. One is that we don't know how to extend this framework to more than two players. This is one thing. And second thing is the issue of credibility, meaning that if a player deviates, it may happen that the other player still is in her best interest to follow the agreement instead of punishing.
Yes. Yeah. So this P, the P is a function which, does it have, I mean, so I don't know this literature, so does it have any specific properties, the P?
No, you can think of it as a scalar here and a term that needs to be determined optimally so that deviation will not take place. So it's really a penalty term here in the usual optimization sense. Okay. Now what I'm presenting here is something linear, but you may have incentive strategies that are highly nonlinear
yes.
In order to account for as many things as we wish. Okay, now this is one line of thought, cooperative equilibria. A second possibility is to look for so-called time-consistent solution. So here the idea is very simple. You consider any player J at any instant of time t, you must check that this inequality holds. And this inequality means simply that the cooperative payoff to go of player J should dominate at least weekly her non-cooperative payoff to go. So if you can verify this for any instant of time t, any player j, you say that the agreement is time consistent. Now here I should mention that this test is carried over along the optimal state trajectory, meaning that at any t that I'm checking for this inequality, the assumption is that from 0 to t, we have been following the agreement. Léon Petrosian was the first to talk about time consistency in differential games. In his writings in Russian, essentially in the 70s and early 80s, he termed this as dynamic stability and individual dynamic rationality. It's really later on that everyone start calling this time consistency. And you have a very large literature in differential games dealing with this time consistency. Some surveys are mentioned here. This is actually a book by David Young and Léon Petrosian dealing with this. Now here we are looking at this inequality along the optimal state trajectory. If you relax this condition of having this inequality holding only along the optimal state trajectory, you get the concept of agreeability due to Kaitala and Pohjola. Here you want to have payoff dominance along any state trajectory and not only along optimal state trajectory. So this is somehow something that we want to have a flavor of larger stability or even outside the path that we have been following. In this case, we have fewer papers. The reason is simply it's much harder to check for these inequalities in this case. One last comment, agreeability, of course, implies time consistency, but not the other way around. Now, this is what I wanted to say about sustaining cooperation in general. Now, let me say a few words regarding the class of games I'm interested in, dynamic games played over event trees. So we know that many problems in economics, engineering, and management science share the following three characteristics. The first one is that we have few agents, meaning that we have strategic interactions. Second, we have some accumulation processes. For instance, so we accumulate knowledge or production capacity or pollution stock. And the third one is that some of the data of the problem are uncertain. So I'm referring here to parameters related to demand, cost functions, the state of the economy, and you name it. Now, if you have the first condition only, you are in the realm of static games. You add the second one, you are in dynamic games, deterministic dynamic games. When we have the three of them, we can talk about stochastic dynamic games as a natural approach. Here, what I would like to highlight is that the stochasticity is not controlled by the players. It's really given as an event tree, which is not the same as in usual stochastic games where players can influence the transitions. So this class of games have been called dynamic games played over event trees. What are the ingredients? We have two sets of ingredients here. One set related to defining the tree, and this is standard, and some other elements related to the game itself. So we have a set of period, capital T period. We have an exogenous stochastic process, an event tree. As usual, when you have an event tree, you have a root node, which is denoted N0. And at each period, you have a set of nodes, N superscript T. So each node NT belonging to this capital NT represent a possible sample value of the history of the process. Why? Because when I am at any particular node, I can trace back the path that I took from the root node to NT. Any node has a unique ancestor, and any node has a set of successors unless it's a terminal node. Using the terminology of stochastic programming, a scenario is referred to as a path going from N0 to terminal node NT. I'll be denoting by pi NT the probability of passing through node NT. So this is all what is needed in terms of defining the tree. Now, the ingredients for the game itself, suppose that we have n players. Each player has a decision variable vector, uj at each node nt. Here, what I would like to highlight, and this is important to see because here there is a difference with usual information structure, the open loop information structure. Namely, here the decision variables are indexed or depend on the nodes, and not only on time, which means that the decisions are adapted to the history of the process. And for this reason, the strategies and equilibrium have been called S-adapted, S for sample and adapted for the idea that decisions are adapted to the history of the process. Now we have state variables. I'll be denoting by x tilde this long vector. We have a value at each node, and we want at all of them, all periods. And we have control variables. I don't think I need to go really through all the notation. It's more or less straightforward, and it will be seen from the context. So I have a transition function that gives me how the state equations are evolving. So essentially at any node, you have a value of state that depend on what the players have done at the antecedent node and from where you are coming to reach this node. We have reward functions at each node nt. So the reward for player j at one particular node depends on the state at this particular node and the vector of actions taken by all the players at this node. At a terminal node, this reward depends only on the state reached here. We are going to discount rewards. So the reward of player J is given by this. What do we have here is a summation over nodes. This is the payoff at this particular node. And I take a sum over periods where I am discounting with this discount factor lambda. It can be assumed to be the same for all players, but it's not needed to be so. Plus the reward that is collected at the terminal nodes. We have some constraints. What is nice with this class of games is that you can accommodate for any type of constraints you may wish, because everything will be done numerically. There is no much room here for doing analytical stuff. Okay. So an admissible strategy is simply a strategy that belongs to the admissible set. Now, if you are used to see the game in normal form, it is easy to define it in the following way. So the payoffs would be given by this Wj for each one of the players. And this is the Jj, which is the total discounted reward here. However, we say that x tilde is obtained from implementing u tilde as the unique solution of the state equations that emanate from the initial state. Meaning here that the payoffs can be expressed as functions of the strategies as usual in a game in strategic form or normal form. Now, the equilibrium I'm interested in is the so-called S-adapted equilibrium. As I mentioned, S for sample, adapted because the decisions are adapted to the nodes. So it's simply an admissible S-adapted strategy profile where you have this condition. So this is the usual condition that you see every time. I'm fixing all other players at their equilibrium value, and I'm best replying as player J. So by writing the game in this normal form and defining the equilibrium in this way, what is nice here is that the existence and uniqueness theorems machinery would apply immediately. I mean, you don't need to invent much new stuff for this. So it's really business as usual. I would like to highlight here one important difference between the S-adapted information structure and the open loop information structure. In an open loop information structure, you would make the same decision for all nodes belonging to the same period, whereas here the decision is really adapted to what is going on in each particular node. So in some sense here, we have an information structure that is not feedback state dependent. However, it's not either open loop. So it's somehow in between the usual open loop and the Markov perfect information structure. So the story of this class of games started in the Middle Ages with my PhD thesis. I was interested
One
in...
question.
Yes, sure.
So in the open loop and this thing, in the S-adapted, do you have examples where they are different?
Yes, yes. It will be seen very clearly because you have different nodes belonging to the same period, and what you are doing at these different nodes are really taking different actions. If you send me an email after the presentation, I would be happy to send you examples where it's clear that open loop is different from what we are getting here with the S-adapted information structure.
Okay. Thank you.
You're welcome. So I was interested here by a model to forecast long-term equilibrium strategies in the European natural gas market. So we had 4 producers, we have consuming regions, and we have long-term contract. And what was stochastic here is really the demand. Now the control variables were the investments and quantities, and the state variables, the reserve of gas, natural gas, and production capacity. So we did this, we computed the equilibria, and the European community used these results apparently in their policy. What was nice is that with my supervisor, Alain Horry, and co-author, we lived enough to check if our predictions here, empirical predictions, realized. So we did the following exercise. We said, let's consider the 15-year forecast that we did, and now we can check the results. And in the worst case scenario, we don't say anything if our results were a disaster, but it happens that we were guessing really quite well. If you look here at the root mean square error in terms of market share, we were doing really good in the different markets. We missed our target in the UK because of some developments in the North Sea, but otherwise it was reasonable. So anyway, there is a literature after that that developed, for instance, regarding computation of equilibria. There is a paper by Horry and Moresino and Siam dealing with this. And there are a number of papers dealing with applications of this DGPET games in energy markets. Now, more recently, we have been interested in developing the theory and extending the theory to other areas, for instance, to the case where we have coupling constraints. So this is the case where the players have to satisfy some joint constraint. And we need to compute, in this case, so-called Rosen equilibrium. Also, some work has been done in incentive equilibria. Now, on the cooperative side, we have a series of papers dealing with sustainability of cooperation over time. And what I'm going to do in the rest of the talk is to give you a sense of how this works by saying few things about these papers with Vishwa, Ekaterina Shevkovskaya, and Elena Paridina, who you can see her next to me on the screen. So let me first, I can change this. No. How can I see the, okay, the title, sorry. So but back to cooperation, how we can mix the two things I'm talking on. So by cooperation, I'm going to mean joint optimization. So what we are going to do is to maximize for the set of players the sum of their payoffs, okay? Now, we do this operation, what we are going to get are the cooperative controls. Now, you can think of this cooperative control vector as the contract to be sustained over time. So this is what we want to do. Now, we get a total cooperative outcome, which can be written like this. So it's simply a W star, which is the sum of what I obtained here. And this is the total amount that we want to allocate to the different players. Now, remember that the game is taking place over time and over nodes. So the question is that how can we allocate this total amount in a way such that all the players will continue the cooperation as time goes. So doing this exercise, what we are getting are essentially three elements: the cooperative controls, the total cooperative outcome, and we can now compute the cooperative state trajectory. You remember from my definition of time consistency that I need to check time consistency along this cooperative trajectory. So I have it now and I can do my testing. So the basic idea here is that in any node, you want each player to find it rational to play the subgame cooperatively rather than switching to some non-cooperative mode of play. Here I'm going to assume that the non-cooperative mode of play is Nash equilibrium. Now, we can see this in an algorithmic way. We define a cooperative game and we compute all characteristic function values. Now, the players choose a solution. It can be a single valued solution like the Shapley value, or it can be the core. And what we get here is either a singleton, one imputation, or a set of imputations. Now, what we need to do at each node, we need to compute cooperative and non-cooperative payoffs to go. And we need to define a so-called imputation distribution procedure such that at each node, this property is satisfied. Okay, so this is the algorithm that needs to be implemented in this setting. So here I have to go through some messy stuff simply to specify the outcomes in the different subgames. So node consistency requires considering payoffs in all subgames. So this is part of the definition itself. So the subgame in node NT, starting in node NT, we know that the value of the state is X star NT. Why? Because the assumption is that we have been cooperating till 10. So the cooperative payoff to go is given by this. If we continue cooperation, we continue to implement the cooperative controls along this trajectory, this is the payoff we get. Now we need to compute a Nash or non-cooperative payoff to go for player J. So here, what you need to see is that, again, the state is the cooperative state, but now I need to recompute the Nash equilibrium that is played in the subgame. So note that the Nash equilibrium here is not the one that was predicted before, because the one that was predicted before is not relevant anymore because it was assumed that players will be non-cooperating down the road. However, they have cooperated till this node. And node consistency means that this green value, which is the cooperative payoff to go, should be at least equal to the non-cooperative payoff to go. Okay, so this is what is going to happen in the rest of the talk is to verify this inequality. Now, I don't know how much the audience is familiar with the details of cooperative games, but anyway, the idea here is that we need to define the cooperative game properly, meaning we have to have a set of players. We need to define a characteristic function. The characteristic function is a mapping from the power set of the set of players into R. So this characteristic function is giving the value, the wealth, or the strategic value of coalition G in the subgame starting at this particular node. Now we can get a set of imputations, meaning that we obtained the total value that the whole the whole set of players can produce, or the grand coalition can produce. And now I want to look at a set of feasible allocations. This is what is called the set of imputations. Now we can pick up from this set of imputations one particular value. So for instance, if we take the Shapley value, you have here the definition. I am not going to go through it. If we take the Shapley value, it means that we know at the initial state and initial node of the game how much player J is entitled to receive in the whole game. And I know this for all players who are participating in the cooperative game. Now, before you get lost, my sole objective here is now to find a trick to allocate this amount over nodes such that this definition of node consistency will hold. Okay, so this is really the what we are after. So then don't be impressed by the notations and all that. In the same way, I can define now the Shapley value for any subgame. So if I am at node NT, I can define a cooperative game starting at this particular node, and I can compute the Shapley value for all players in this particular subgame. Once this is said, is done, we need now to allocate over nodes the total amount that each player is entitled to in the solution that we chose. In particular, if it's the Shapley value, I have to decouple it over nodes. For this reason, we introduced the so-called imputation distribution procedure. So this is these are functions that are defined along the cooperative state trajectories for each node, each instant of time, and each player. So we say that an imputation distribution procedure is node consistent at initial state and node if at any position down the road we have these conditions. One, feasibility. It means that what I have allocated using this distribution procedure till instant of time t-1 is given by this. Now, if I continue, I should get the Shapley value in the subgame starting at this particular node. And it has to be individual, the solution has to be individually rational, but we are getting it for free here because Shapley value is an imputation, okay? So the contract here I have is simply to find these time functions that satisfy this requirement. And this is given by the following theorem, which says that for any time period, t from 0 to t-1, if I define this beta function along the state trajectory in the following way, at each node, given the state value at this node, I will give to player J the Shapley value in the subgame minus this term. And this term is simply the conditional probability that we hit this node at t plus 1, knowing that we are coming from this node t and this Shapley value. Okay, and of course at the terminal node, since we do not have decisions, it's straightforward to give each player the Shapley value in the cooperative game played at this terminal stage.
So one question.
Yes, sure.
Suppose if a player at in the middle of the horizon, like at some intermediate point, if he decides not to cooperate, so how do you ensure that such a deviation won't happen by a player?
By giving this player this amount at each node, I am sure that now I have individual rationality, meaning that player J will get a payoff larger in continuing cooperation than in moving to non-cooperation. So this is the idea of cooperation dominating non-cooperation along the cooperative state trajectory. This is the very meaning of time consistency.
George, so could we also say that this is a way for implementing Shapley value in a dynamic manner?
Yes, this is you can look at it in this way. Mm-hmm.
Yeah, it's in that sense, it's a very nice result because it's not only a dynamic implementation, but you're also showing that it can depend on the state variables. So even if you have evolution, it's not even just a static dynamic implementation. You can implement it with the appropriate penalty function in a consistent manner over time. So it's a very nice result.
Yeah, thank you. You are absolutely right. Actually, what I would like to highlight here is that this formula or this theorem applies whatever are the primitives that we are considering. So whatever is the reward function, the payoff cost function, demand function, whatever they are, we are having this result, of course, modulo the existence of solution, equilibria, etc. Okay. So this is one case of ensuring time consistency in this class of games when we use Shapley value. Now, everything can be done also for the core. Actually, it can be done for any cooperative game solution. However, for the core, it's a little bit messier because the core is a set value solution. So now the question we should ask ourselves is that we are following an imputation in the core, but in the subgame, what are we going to do, especially if it happens that in the subgame, the core is empty? Okay, so we will have questions to deal with here that are a little bit touchier. But anyway, we can really follow the same procedure. Maybe I will not go through all the details here, but I would be happy to answer any questions that you may have. So the idea here as a starting point is that the players must agree on one particular imputation in the core if the core is not empty. Of course, if the core is empty, I can stop my presentation here. I can do nothing about it within this framework. But assuming that the core in the original game is not empty, now what we are asking the players is the favor of giving us one imputation. And of course, we can repeat the exercise for any imputation they may have chosen. So the conditions here can be worked out through the same procedure as I showed before, defining an imputation, meaning what is the imputation distribution procedure, etc. And we end up with a theorem which is relatively similar to what we got in the Shapley value. However, here the theorem is saying that for certain imputation in the core, in the original core, I can find a way of allocating this imputation over periods and over nodes such that we have time consistency. And recall that time consistency means that players are will stick to continuing cooperation at each node down the road instead of moving to non-cooperation. So we can get a similar result here in the sense that we obtain a formula for doing it. And again, this formula is independent on the primitives of the game itself. Here we can get some very nice results. And for those of you who are familiar with what Shander and Tulkens have done with the gamma core, we have here some interesting relationship of the same kind. So we can establish a relationship between the rewards and the node consistency. So for instance, here the beta.
George, you have a question in the chat?
Yes.
There's a question in the chat.
Where can I see it?
Anirban, do you want to say out the question? Do you want to give out your question? Okay, maybe I'll read it. It says, can there be a DGPET that does not have a super additive convex characteristic function? How do we handle that? Because Shapley value may not make sense in that case.
Yes, this is a much more general question than the question I'm dealing with it here. Here, the idea is very simple. Given a Shapley value, what should I do in order to sustain cooperation over the tree and over the dynamic game? So I'm not really looking at the characteristics themselves of the cooperative game, whether they are super additive or not. So this is somehow an outside question of what we are doing here. But if Shapley value makes sense to the players involved in this cooperative game, this is the way to go in order to ensure sustainability. Similarly, for instance, when the core is empty, we can think about some procedures like defining epsilon core and things like that in order to correct for what is missing. But again, here the main point is that assuming that this core is non-empty and the players are selecting this particular imputation, how do we decouple it over time? How do we define payments over time such that we have time consistency? Okay. Any other questions? No? Okay, so what I was saying here, that the payment that goes to player J in this particular node is related to the reward that this player is getting, plus a certain omega j here. And this omega j is a transfer that this player is getting at this particular node. And what is interesting to note here is that the transfers are balanced, meaning that at any node, the sum of these transfers is equal to 0. So we are not, in some sense, borrowing from one period to another. Everything is done at any particular node. So let me finish with some comments on this node consistency. The results I presented can be implemented for any characteristic function you may pick up. Here we're assuming essentially that players who are not part of the coalitions are reacting a la Nash, but it can be the alpha characteristic function, beta, so on and so forth. Of course, in what I was doing, I was assuming that a Nash equilibrium exists and I have a unique Nash equilibrium, meaning that the players are selecting this Nash equilibrium. What we have been doing in this research program is not to solve the selection of equilibrium problem. What we are saying is that given some initial agreement, what can be done in order to sustain this agreement over time. Similarly, if the core is empty, this is a completely different story that needs to be dealt with elsewhere. Okay, So this is one line of thinking. The second line of thinking is, as we said, we can follow this idea of the implementing a cooperative equilibrium. However, here this theory of dynamic games played over event trees was developed essentially for finite planning horizons. And we know that when you have a finite planning horizon, it's not feasible to implement a cooperative equilibrium. So for this reason, we are after an epsilon cooperative equilibrium. So here the idea is that if a player deviates from cooperation, then all other players will punish this deviator by min-maxing her payoff. This is one possibility, but you can do the punishing differently by playing Nash or doing something else. Anyway, here in this framework, as you know, history matters, and so the idea is to look for non-Markovian strategies, strategies that remember what the player has done during the history of play in order to look for these punishing strategies. Given that I'm left with maybe 5-10 minutes, let me give you a brief account of what we have done here. Again, the paper is available, and if you are interested, we can discuss it offline. I mean, after this presentation. So here the idea is to define behavior strategies that map the history of the node into the control set. Now we can write the payoff of any player in the subgame as a function of the controls and what's happening here. To save on notation, we will be writing it as function of sigma. And here is the usual machinery to define an epsilon equilibrium. So here the dominance is not assuming epsilon is 0 as usual. So we tolerate an epsilon here. And as I said, players are min-maxing the deviator payoff. We develop green trigger strategy behavior here. It says essentially as usual that if the players have been following the agreements throughout the history of the node, player will be implementing also her part of the agreement. Otherwise, we resort to punishing strategies. And the final outcome here is that we can characterize an perfect epsilon equilibrium in this class of games, where this epsilon is defined in the following way. So you have to look at, to define for each node an epsilon, and after that you take the maximum over all nodes, over all near periods, and all over players to get this this epsilon that is defining the epsilon equilibrium. And this epsilon equilibrium is obtained by this maximum. Here, maybe you don't see that some of the parentheses are in red, but essentially it's based on computing the differences between when the players are implementing the cooperative agreements and when they are deviating. So this is the usual trick to get this epsilon. And we are fully able to characterize this perfect epsilon equilibrium trigger strategies. We have also some examples. Here is an example from environmental economics. So suppose that you have 3 players, and this is a pollution games. So at each node, the players are polluting these quantities. And what we have is a dynamical system describing the evolution of pollution over nodes. So the stock of pollution at this particular node is the sum of what the players polluted in the antecedent node plus what was still in the environment. So the delta is the nature absorption rate. Now for a simple illustration of the theory we are developing, suppose that the uncertainty here is related to this absorption rate, and let us consider only two possible values, delta underbar, delta upper bar, and everything else is given. So we have a so-called damage cost. So each player will be paying this cost that depends on the stock of pollution in the node, and we have some emission cost. So what we do here is to consider a simple tree. So you have the initial node, and after any node, you can go left or right. So we have a binary node. So we do the computations, and this is what we get for epsilon. So this is what I want to highlight. So starting period t, player one has to be bribed by this epsilon in order to continue cooperation. And we know that in the last period, cooperation breaks down because we are in a finite horizon. So what we can determine here is the different values of the epsilon in the different nodes. So the question that was raised before, the difference, for instance, between open loop and as-adapted information structure is clearly seen here. These four nodes belong to the same period, but the values that we are getting are very, very different from one node to another. Anyway, we can determine this epsilon for any tree. Again, here we are taking a much larger tree. And what we see here is that for the 7 first periods from 0 to 6, all players are implementing their cooperative part of the agreement, and it's really towards the end that we see that I want to deviate. This is a classical result when you have finitely many time repeated games, but here on the top of having the repetition, you have state variables. But anyway, we see that towards the end, there is a deviation for player one in period 7, 8, 9, whereas the other two players are deviating only in period 9. So this gives you somehow the tools in order to design an environmental agreement that can be sustained during the whole planning horizon. But anyway, from a policy perspective, you know that this agreement is sustained at least till period 6. So now you may put in the agreement something that will tell after period 6, we will look what is going to happen later on. So this is a simple illustration of what we can do. Let me mention a couple of extensions. We are working on the case with non-transferable utility. So this is a paper with Elena and Vishwa, the deterministic case, and we are working on extending it to a stochastic case. I have a paper with Elena regarding what would happen if we have different opinions about the tree itself. So here what we have assumed so far in all our research with the friends here is that the transitions from one node to another are given by nature. Now, what would happen if nature is telling the different players different things about these transitions? So the question is how to aggregate opinions, and we have some results in this area. We are working on a book with Elena and Vishwa on this class of dynamic games played over event trees. We are covering both cooperation and non-cooperation, and we hope to publish it in 2021. Now, I don't know if I have some PhD students listening. What I want to highlight here that this class of games has many applications in supply chains and environmental economics. I mean, you can think a lot of issues related to coordinations and competition supply chains in environmental economics, designing agreements, sustaining cooperation in different types of pollution situations. So the framework leads itself really to some nice applications. At least this is what I believe. So thank you. I'm going to stop here. Sorry for rushing towards the end. But again, the idea is to give you some information, and would be more than happy to continue the discussion now or after or through emails. So again, thank you for listening, and thank you for the invitation. I would be happy to take questions if you have some.
Thank you. Yeah, so we have time, so we can have some questions.
Sure.
I have some questions. Can I ask? Yeah.
Sure.
So, yeah, I have one question about incentive strategies. So what was done by Hämäläinen and Adamo, it was for differential game or discrete time games? Because when you have discrete time, you can punish, so you can adopt punishment only after one period, because you cannot react at the same time period, because you cannot observe the strategies. So this is done, these incentive strategies are done for differential games. Initially,
they did both in the sense
both?
that yes. So they defined incentive strategies in the case where you don't have delays in observing the deviation, and the case where you have delays in observing the deviation.
So even in discrete time, they assume that you observe strategies, yes, at this time period.
You observe deviation if it happens only one period after.
Only one period after. Okay. Understand. And what another question? What do you think? So you tell about sustainability when players deviate. So this is like reasonable deviations. But what do you think? Is it interesting to consider like sustainability over stochastic deviations? So stochasticity may be something like wrong. You have 3, but it may be wrong, or it may be corrected after some periods. And do you think for example, cooperative strategies are stable in some sense to the deviations of stochasticity? Is it interesting to consider? What do you think?
I think here this is something that has been done within the framework of cooperative equilibria. There is this very nice paper by Green and Porter in Econometrica, where they are looking at a case that what would happen if you don't know if the result is not actually, the result does not correspond to the agreement, but you don't know if it is because a deviation or because it's due to some stochastic event. And their conclusion is that you need to punish anyway, because if you don't punish, players will hide behind the stochasticity. So I think this idea was studied already, not in this kind of framework. It would be interesting to look at how it can be cast in a framework like this one.
Yeah, it's an old paper also, and indeed, Green and Porter has been around for quite some time now. Yeah.
Thank you.
Welcome. Any other questions?
I have one, but I will see if somebody else has one. Okay, so actually I have 2. So the one was, suppose you don't have uniqueness. You can take any one of the 2 equilibria or 3 equilibria. I mean, since we are talking about cooperation, most likely you have unique equilibria anyway, otherwise the games are not interesting. But you could take any one of the equilibria and implement this. Am I not correct? You could take one of the 2 Nash equilibria and implement it.
Sure. I mean, here the idea is that simply you need to connect the pieces over time in a way that you can get the initial value that is given to a player from the outset. So for instance, you are playing the game from 0 to capital T. At 0, players can compute what would they get if the game is played cooperatively during the whole period. Now, if we are at a node and we have multiple equilibria, as I said, we cannot say much here about which equilibrium to select, but what we can do is that if you select an equilibrium, or if the set of players agree on one equilibrium, we can continue using this machinery.
So the other question was, so suppose I was actually, instead of nature choosing the event tree. So suppose I was thinking of the tree structure and actually we were making deliberate decisions. Could we think about applying something like Meyerson value, because that already gives, or something like a position value, because that already gives some payoff based on the network structure. So that would directly align the tree structure to payoffs in some ways.
Excellent question, but I cannot say immediately what would be the implication. But this is a very good idea to think about in the future. Yes, but I cannot really come out here with a very clear answer regarding this one. Because in this framework, although we were able to deal with the case where the probabilities, the transitions are not the same for every player, but I don't know how we can manage if the tree is somehow not defined in a clear way or in a straightforward manner. I really don't know, but excellent question.
Other questions? Well, so I think if you want to stay and people want to chat, so usually we also allow that at the end. If people want to chat for a little bit, feel free. Those who want to leave can leave. Yeah, so you can do the stop sharing, and people can just chat, because also it's friends at some point. So